What are we going to do? We are going to be describing a function graph. But we're going to be using the first derivative to help us do it. Which means that we are going to be doing exactly the process we did in Unit 3, which was, let's talk about where a function is increasing, let's talk about where a function is decreasing, let's talk about where there's relative mins and maxes, but let's do that without actually looking at the graph of the function. Let's do that by looking at the function's derivative. Let's predict those behaviors through analysis rather than describe. So predicting would probably be a better word. Describing is kind of what you do in pre-calc. You're like, here's a picture, and we describe it. In calculus, we straight up predict it. We tell you what it's going to look like before we even look at it. So that means, specifically, what we're going to do is figure out where a particular function is increasing and decreasing, where it has any relative maxes or relative mins. So actually, if you do have to take that quiz, this isn't a bad review because this is a part of what you had to do on that quiz. And so all of those come from looking at the first derivative, set equal to 0, generating critical values or critical numbers, and then we make that number line sign chart. You guys have lots and lots of experience that with polynomials. Okay. My AB students, they're learning, all the AB students, they're just learning that. They're doing it with a lot of different kinds of functions though. They're using trig functions and other things. But they're just starting it. So you guys have definitely more experience doing this and understanding how to read the number line. So you could help them with that if they needed it. We're going to do this now with an exponential function and not a polynomial function. So what that's going to mean is, while the steps are the same steps, they're going to flow a little differently when you start with something that has an exponential function versus a cubic function that turns into a squared when you take a first derivative, okay? Or a fourth degree that turns into a third degree. Everything we did with polynomial stuff. Now we're going to roll this with an exponential function. The analogy I used in second period was, this is going to look really scary. It's going to be like the first time you watch a scary movie and you kind of don't know where the scary parts are. So they really startle you and okay? But then later on, if you watch that same movie like 17,000 times, it's not scary almost anymore. I mean, you kind of know what's going to happen. This is going to be the same thing. It's going to look really kind of scary at first. Some of the parts are going to look scary, but after we do one and then you try another one and we try another one, then you're like, okay, not quite as scary. I think I got it. I'm a little numb to it. So with all of that said, let's take this guy, x squared times e to the negative x, and we're going to analyze him. So if you would please take x squared times e to the negative x and write the derivative. A little bit of product rule, which we're good at. I know you probably wouldn't have believed it when I was teaching you product rule the first time, but you guys are like product rule experts now. You're like, product rule? No worries. I rolled out in my sleep. and may roll in. All right. Product rule. Product rule is a lot more forgiving than quotient rule. For quotient rule, if you do it in the wrong order, you're wrong. Product rule, you can kind of go either way. As long as you remember to keep one piece of the product, one factor of the product the same, and the other piece its derivative. That's really the only way you can mess up. Sometimes it's easy with ease, though, because you kind of, when you're taking the derivative, it just looks the same. So let's see. G, F prime, F, and now G prime. So e to the negative x times negative 1. Okay. So we should all... Hey guys, what are we doing? Yeah, I kind of don't even want to know. Just stop. Okay, thanks. So product rule, we should be hopefully pretty good at that and should be able to put the pieces together. And the new part for e to the negative x, remembering how to take the derivative of that, e to the negative x being e to the negative x times negative 1. That's that chain rule for taking the derivative of e. Derivative of e to any power is going to be e to that power times the derivative of what's in the power. So, f prime, the derivative, cool. F prime equal to 0, that's the part you're probably not feeling super cool about. That's usually where we get the boogeyman jumping out at us or whatever. Because that, you look at that and go, why, what? How am I even supposed to do that? You know, you're pretty conditioned, trained, comfortable with factoring a quadratic and getting solutions, doing a GCF on a polynomial and getting solutions. Those are kind of the two things we've done a lot. And so when I tell you we're going to set something equal to 0, your typical algebra stuff, when you look at this, kind of, you freak out because it's got e's in there. Okay. I'm going to factor this. I'm going to do a GCF kind of factoring. I'm going to take all the common factors out of this chunk and this chunk. And so here's what I see when I'm looking at common factors. They both have an e to the negative x. Okay. And so I'm going to put an e to the negative x on the outside of a set of parentheses. Now, before we go any further, I'm just going to stick with that part right now because, and this is just, I think it is totally psychological. You guys are going to go, ah, what? Okay, but if I did this, and I said, all right, guys, we got this piece and we got this piece, and we're going to pull a 5 out. Sorry. I'm fairly sure you'd be okay with it. A 5 out of both of these, you'd be like, okay, yep. So, e to the negative x out of both of them, you're like, oh, it's because it's scary looking. It's a scary looking 5. That's all it is. It's a number. It's a term. It's a factor. I guess that's the best thing. It's a factor, just like a 5 would be a factor. Just like if these had squiggles in them, I could might take a squiggle out of this guy and a squiggle out of this guy. I might take a heart out of this guy and a heart out of this guy. That sounds kind of gross. I might take whatever out of this and out of this. Anything they have in common as factors, I can pull out to the outside. So the e to the negative x, even though I don't know how it's gonna affect things maybe, and I'm a little worried about having to work with it, it's still something they have in common. Okay? So it's a common factor getting pulled out of both. And the other common factor I can pull out of both is an x. So I can pull out an e to the negative x and an e to the negative x. And this x will then take that x squared down to a single x. So that would leave me with just 2 plus x times negative 1. And I'm going to just write that a little prettier. All right. Now, let's let that percolate for a minute. We factored stuff out of both chunks. We factored e to the negative x out of both chunks. We factored x out of both chunks. Just like if we were looking at this, we would factor a 5 out, and we would factor an x out, and we would be looking at something similar. It's just a scarier looking 5. So we got to condition ourselves to not run screaming when we see an e to the negative x or e to whatever, because what we're going to find out here is that he's actually a pretty friendly guy to be our factor. He is not going to make this problem tough at all. And I know you're going, you're lying. And it's not even because we have a calculator, because even without a calculator, you should still be able to, we can still work with e to the negative x. Okay, how are we? Yes? How are we on the factoring? Yeah, don't love it, right? But when it's, Cameron, when you're here with a 5, better? Yeah, so it's just like, okay, it's just a scary 5. It's just something, and you know what? If we're going to do these problems with e's in them, this is gonna happen. We're gonna end up with e expressions in both chunks after we do a product rule, and we'll pull an e expression out. So it's just like I said, you're gonna get used to it. Okay. Boop, boop. So what are we doing? We're taking the derivative. We're gonna set it equal to 0. We're trying to solve that to get critical values. So I'm in the midst of the solving part, which is not really a calculus thing. This is more of an algebra thing, but honestly, I know we don't do enough solving with e's in our pre-calculus curriculum. All right, I got this times that times that. So 2 plus negative x equals 0 will generate a critical value. X equal to 0 generates a critical value of 0. E to the negative x equals 0 is the other thing I have to consider. It's just like before. I have my derivative written in factors. I'm going to look at each of my factors potentially equal to 0 to see what the critical numbers would be. This is the one that you're probably thinking, nope, don't know how I'm going to do that. But what I'm about to tell you will help you make it a lot easier. This one, though, before we do that, if x is 0, x is 0. Okay, x equals 0 is a critical value. Hooray. This one, well, if 2 plus negative x equals 0, then negative x, if you subtract 2 from both sides, would equal negative 2. So divide by negative 1, x equals 2, and that's a critical value. Or you just look at that and go, oh, if I put a 2 in for x, 2 plus negative 2 makes a 0. You don't necessarily have to do steps to get that critical value of 2. Those guys are fine. Here's the one you're scared about, right? Well, here I'm here to eliminate your fears. Now and forever, e to any power of x equals to 0, not going to happen. Never has a solution. E to the 5x equals 0, no solution. E to the x plus 3 equals 0, no solution. E to the, and that was x plus 3 up in the exponent. E to the negative x equals 0, no solution. No matter what number you put in here for x, e to a power is positive. Now, I know you're kind of going, well, wait, like what if, but let's think about it. You know, even if you did have something like that, that's not negative. That's this. And e to the 5th is not negative. So 1 over to the e to the 5th is not negative. It's not negative, so it's definitely not 0. Right? It can't even be negative. If we actually put, you're like, well, what if we put a 0? Well, can't do that. I mean, you can't do that and get 0 because it's 1. Now, if you want a little bit of convincing, how about I do this for you? Right. There's the graph for e to the negative x. And just like all e curves, it's got that J shape. It's a negative x and not a positive x, so it's flipped the other way. But take a look at this and remember, you're like, oh yeah, that's right. It's got an asymptote along the x-axis. It never goes negative. No matter what I do, oops, I got to make sure it's all up in the exponent. Oh, they hate me. I'm just not even. Forget it. I'm just gonna leave it. No matter what I do up in that exponent, if I could do anything else, I would. No matter what I do up in that exponent, I'll do that, okay? However I turn that exponent around and do whatever to that exponent, it's still not going to go under the x-axis. E to any power never equals 0 or goes through the x-axis to become negative. It just doesn't happen. So he's a factor, but he gives me no critical values. That's a win. So when I get to this part, start making my number line sign chart. Okay. Here I go. My derivative was e to the negative x times 2 minus x. And my number line is going to be 0 and 2. E to the negative x, e to any power of x, never negative. You knew that, but you never really thought about or cared about it. It's never negative, so it's never 0, essentially. E to the negative x equal to 0, no solution. And e to the negative x is always positive. So here's how that's going to help me do this next part. Because we're super close to being finished. All I got to figure out is how the number line works for this guy. And then I'll have all the information I'll need to answer these questions. Or to make these descriptions, to make these predictions. So I'm going to take my number line and I'm going to pick some numbers in the intervals. And I'm going to analyze my derivative. I'm going to look at e to the negative x times 2 minus x when x is -1. So if I was going to make a little table here, I'd say, okay, let me try a -1, let me try a 1, let me try a 3, let me see what's going to happen to this. Get rid of that mess. And I can use my calculator if I want, but I can also use some thinking. Because here's what happens. E to the negative x, and this is part of this is we have to do this without a calculator in AB, so that's why I tend to lean to do this without a calculator. Could you take this and plug -1 in and type it in your calculator and see what happens? Sure you could. You could put a -1 in, you could put a +1 in, you could put a +3 in, get these signs for these pieces, be ready to go. But e to the negative x is always positive. If I put a -1 in, that x that's there is negative because it would be -1. 2 minus -1 would end up as +3. And so the ultimate, I don't know why I wrote a plus sign there. I meant to write an answer. So the answer to that product would be negative. When I put a +1 in, the x that's would be +1 would be positive. E to the negative x, always positive. 2 minus 1 is positive. So that's a positive result. And then the 3, e to the negative x, always positive. A +3 for x is positive. 2 minus 3 would be negative. That would be a negative result. And take a look. We have alternating. We're not always going to have it, but we do have it for this one. Every step is to get to this number line is something we've learned before. The twist is we're doing this with the e function in there now, with that exponential function. So, like I said, I tend to focus on doing this without a calculator because we have to do it without a calculator in AB. So that just, my instinct goes to doing it, and in pre-calc. So anytime I'm doing a number line chart like this, I tend to be doing it without a calculator. And I'm too lazy to type all that in my calculator. But if you want to, go type it in. E to the -1 times -1 times 2 minus -1. As long as you're careful, you should get the same results I get. And then we are finally ready to write some conclusions, predictions, descriptions. So here are the conclusions I'm going to make about this function. My function that I started with is decreasing from -infinity to 0. And then again from 2 to infinity. My function is increasing from 0 to 2. My function has a relative minimum, and I'm doing that first because it's first on the number line this time. My minimum happens at 0 because I go from decreasing to increasing. Decreasing to increasing makes a min. And then, but we need the sign change. You know, if it was negative, then we wouldn't have a min. Positive to negative, uphill to downhill makes a max. Oops, that's not what I want either. Now, we don't want to, I don't want you to not use calculus to do this, because that is the purpose of the exercise. However, I also want you to have some idea of whether what you did is accurate or not. So a nice way to do that, since we've got the technology, oops, I did that the same thing I did in second period yesterday. So the good plan is, well, let's actually look and see what this looks like. These are all my conclusions I've made. Let's see if they're accurate. Right. So here is the graph for x squared times e to the x. I'm going to back out of that a little bit. That's kind of fun. And you can see how that might be used for a function model. You know, you can see how a set of data could go like this and then like this. And maybe, you know, where it doesn't have the same kind of symmetry that sometimes polynomials have, where this curve coming up, but then this curve coming down is a lot longer. So that's sort of the combination of the x squared and the e to the x. But just based on my descriptions, yep, decreasing, increasing, and then it starts going downhill. And then if we click on it, Desmos verifies for us. Move my arrows. All right. Click on the graph. Desmos verifies for us by highlighting that this minimum point, this change from decreasing to increasing, is at 0. And that this change from increasing to decreasing is at 2. Never mind, I was thinking about something else. So in Unit 3, we also did concavity and points of inflection. That's a lot harder with this kind of function. Our second derivative would be a lot more complicated. It's a lot harder to get critical values. Essentially, you have to basically go to technology to do it. It's not impossible, but we probably wouldn't apply it. We wouldn't do it the same way we would do the first derivative. Even in AB, we would use technology. But just sort of informally, we can see, I bet there's an inflection point somewhere there, because when I'm looking at, I see some concave upness and then some concave downness, much subtler concave downness than concave upness, but we definitely have some concave up and then some concave down, so we have an inflection point. This would even be a diminishing return point specifically, because it's going concave up to concave up. So here, my first derivative positive and my second derivative is positive. It's growing and the rate of growth is growing. Here, it's still growing, whatever this could model, but the rate of growth is slowing down. It's flattening out. And then it kind of looks like it keeps, no, it doesn't. And it's going to move. It's not going to hold that pen with it. I know there's a way to lock the pen in. I'm not going to play around with that right this second. But if I move it, just ignore all my messiness, it looks like we do have another inflection point, because it does. It comes down, but then it kind of seems like it turns. So we have an inflection point maybe somewhere in here too. We could find them. They're not quite as easy to do analytically, though. This derivative, the second derivative here, would be a pretty hot mess, because we'd have to do, like, from here to here, we'd have to do like a 2-part product rule. We'd have to basically have to do a product rule on this part and a product rule on this part. So we would have 4 pieces. I don't know, we could probably do it. It would probably be, I don't know. I'm curious about it. I probably want to sit here and do it, but I'm not going to do it in front of you guys because I know you'll just be like, you're killing me. Okay. All right. So that's your process. That's what we're looking for. That's what we're aiming to be able to do ourselves. Okay. And so I'm going to give you one of those to do. In addition to that, I'm going to give you another tangent line to do, couple more derivatives to do, and I've got all of that already set up for you on our fourth period page. So if you go to our fourth period Schoology page, if you decide to, and you look, here's the assignment from last class. Here's the assignment for this class. This is another chunk of problems out of the textbook we have access to. This is technically page 307. And we've got some exponential functions here. We've got some tangent line questions here. We've got graph questions here. It's actually asking us to do more than what we did. It's saying to do extrema, inflection points also, asymptotes also. We're just doing extrema with increasing and decreasing. And so description of the assignment, 4 problems, 36, 39, 42, and 45. 36, 39, 42, and 45. 36 and 39, just find the derivative. Okay. 42, let me get rid of all that circling, make sure I can see everybody before I circle. So 36 and 39, you're just finding the derivative. 42, you're doing the tangent line, and then 45 is the analysis. So I would work backwards. That would just be me. And I would do 45 first, because that's what we just talked about, and see if I can handle it. Get help if you need it. And then the tangent line for 42, and then just write me some derivatives on 39 and 36. All right. That is your quest.